Our final application of equilibrium is solubility. We'll mainly think about the solubility of ionic compounds, cations and anions held in place in the solid that can dissolve and break up into their ions, just as we've dealt with acidic, basic, and neutral salts earlier on in the class. This is another area where just remembering those polyatomic ions is really important, because when you see a salt or an ionic compound, you need to know what it's going to dissociate into. So recall all of those polyatomic ions that we have. Just a review of what is happening when something goes into solution. So NaCl is held in place by these strong ionic bonds, the strong electrostatic forces between sodium plus and chloride minus. It's actually sort of incredible that water is able to overcome those strong forces, because it's such a polar molecule. The negative charge on oxygen is able to sort of surround each positive ion, and the partial positives on this hydrogen are able to surround the chlorine and stabilize both of those individual charged particles and bring them into solution as individual ions. The one-way arrow here indicates that this is a process that, for the most part, goes pretty much to completion. We can dissolve a lot of NaCl into water before we reach a sort of equilibrium state. Again, review of that prior chemistry. If we think about ionic compounds, they would be insulating in the solid phase, but once they turn into a liquid, they would be conductive, and when they go into solution, those individual ions make the solution conductive. In contrast, if we have something that's a molecular compound like water, sugar, any of the other just normal molecular compounds in water, that will be basically non-conducting. The terminology, which is again a bit of a review: electrolytes, that's something that produces ions when dissolved in water. Strong electrolytes are those that completely dissociate, so that's all of our ionic compounds and our strong acids. Our weak acids and bases are weak electrolytes that only partially dissociate or partially produce ions in water. The key thing that we're going to calculate here is this quantity called the solubility. That's the amount of a particular substance that can be dissolved in the solvent, which in our case is going to be water. So it's how many moles of solute, of moles of some ionic compound, say, will dissolve in 1 liter of solution. In general, some compounds are highly soluble, so the solubility might be 2 or 3 or 5 moles per liter. Some things have very, very low solubilities, however. So our solubility rules just sort of makes a categorical yes or no assessment to each compound, rather than dealing with calculating the individual solubility. If the solubility is relatively high, we'll call it soluble. If the solubility is relatively low, we'll say that it's largely insoluble. So mostly what happens is it precipitates out of solution as the solid, as you've seen in lab before. So for something like lead chloride here, PbCl2, we can think about both the solid dissolving in water, this dissolution reaction, as well as we could always think about the precipitation reaction. That's sort of the reverse reaction, the individual ions coming together to form the solid. In this case, according to our solubility rules, both lead chloride and barium sulfate are insoluble. But again, when we analyze this from the perspective of equilibrium, there is going to be some equilibrium here. So even though we mainly see lead chloride as the solid, when it goes into, when we try to mix things and try to get those ions into solution, it mainly is going to stay precipitated out as the solid. We will get a small amount of lead 2+ ions and a small amount of Cl- ions formed in solution. That's really important because lead, even at incredibly low concentrations, is very, very hazardous to human health. So even though most of the lead will be precipitated out of solution, a little bit will be dissolved, and that might be incredibly harmful. The same for many other compounds, where even at low levels, they might have a very big impact on the chemistry of our solution. So with that preface, we can use our normal equilibrium principles to calculate solubility, just like we could calculate pH, just like we could calculate the equilibrium concentration of any other process. In this case, just like for an acid, we always think about the Ka reaction. For an ionic compound, what we're going to think about is always the dissolution reaction, the solid going into solution and dissociating into its cations and anions. So we always write the solid as the reactant, and then the individual cations and anions are going to be the products. So those are going to be aqueous there. And we label this reaction KSP for solubility product. So here's an example. Silver sulfate here on the left. Silver is always a +1 cation. Sulfate you should recognize as SO4 2-, and so the solid that we're thinking about, because each Ag has a +1 charge and each sulfate has a 2- charge, the solid here is Ag2SO4, and that's the ionic solid. Then the ions that it breaks into, well, the cation is silver. There's 2 of those silver ions, so it's going to break up into 2 Ag plus ions, Aq, plus the sulfate is the other ion. There's just 1 of those ions, plus an SO4 2- ion. And again, for this, the K for this reaction is KSP for Ag2SO4. We can look it up in a table of solubility products or a table of KSPs, just like we could look up a weak acid in a table of Kas. When we think about K equals Q for this reaction, in this case the KSP is equal to 1.2 times 10 to the negative 5, and the Q is just the product, so Ag plus squared because of that coefficient of 2. Even if we've been doing a lot of acid-base equilibria where the coefficients are usually 1, definitely remember to use those coefficients here. So 2 means that we have an exponent of 2, and 1 SO4 2- ion. Again, a solid doesn't have a variable concentration, so it doesn't show up in our equilibrium expression, just like pure water never showed up in our Ka or Kb equilibrium reaction quotient. Just like for weak acids and bases, we're mainly going to think about cases where KSP is much less than 1. So this reaction is going to lie mainly towards reactants. Thinking again about that sort of number line approach, where the bigger that K is, the more this reaction goes towards products. Products are over here on the right in our reaction and on our number line. The more products we make, the bigger that K is going to be. These cases, though, again, we're always going to be a case where we only make a small amount of products here. Again, really important to know those polyatomic ions and their charges so that you can properly write out the products of these. Again, some people will try to write water as a reactant here. You can see we don't do that. Water is present, but the only place water is present is sort of implicitly in the AQ sub phase there. There's no reaction with water, like an acid-base reaction with water, for example here. The water is just present sort of surrounding each of these individual ions and helping pull them into solution. So the only place we need water is that AQ phase of the products. Again, it's really just another application of equilibrium. We definitely need to remember coefficients again, because we'll have a lot of cases where things aren't equal to 1. 2Ag plus, so we've got a squared term there. Remember, we'll also use the coefficients in the change row of our ice table. Now let's use that to actually calculate a molar solubility. The great thing here, nothing really new. We're just going to use our normal equilibrium procedure, but now what we're going to calculate is the molar solubility, basically how much of this solid is going to dissolve. So we have to first write our balanced reaction. In this case, we're always going to use the KSP reaction. We're never going to write anything where it like reacts with water or another salt or anything like that, just the KSP reaction. Just like for a weak acid, we always write the Ka reaction. That's going to be how we calculate the pH. So here, for this example, we're thinking about calcium hydroxide, CaOH2. So that's our solid starting material, CaOH2, solid. We're going to go through the normal equilibrium steps, writing out the reaction, setting up our ice table, all of that. That's a solid. Then the products are, the positive ion is Ca. That has a 2+ charge because it's in group 2. Plus the other products here, it's OH is the hydroxide ion, and we can see that there's 2 of them. So plus 2 OH minus. That is our KSP equilibrium here. Now we should write K equals Q. So KSP here is equal to Q, which again, it gives us the KSP value. That's 5.0 times 10 to the minus 6 is equal to, then the reaction quotient here is Ca2 plus times OH minus, and again, we've got that coefficient of 2, so OH minus squared. Next, we're going to go to our ice table. To set up our ice table, the only new thing we want to think about here, this is in pure water, so we didn't have any of these ions to start with, 0 of each of the products. This is a solid, so in terms of concentration, its concentration is constant. The only thing we might do here is put in a minus either S or minus X in the change row to emphasize that when we start out here, we didn't have any CaOH2 dissolved, but we are going to dissolve S moles per liter of the solid. That is going to dissolve. It doesn't change the concentration, but it is an important thing to keep track of because this minus S is just equal to our solubility. So S is the molar solubility that we want to calculate. Again, just the S or the normal X in our ice table. With that slight addition, just that the X or S that we calculate is the solubility. Now we write out the products here. Well, Ca2 plus is going to get a plus S. And OH minus, again, because of that 2, is going to get a plus 2S. I often just do this with X rather than S, but for this one here, just to emphasize that it's molar solubility, we're going to use S rather than X for this one table. Now we have our K equals Q, we have our ice table, we can plug in and start to figure out what method we wanted to use to solve. So we can say 5.0 times 10 to the minus 6 is equal to Ca2 plus is S, OH minus is 2S. Again, a little bit hard to read with S looking a little bit like a 5 there. And that 2S is squared. Next, we want to think about choosing a method to solve here. Since KSP is small, we know that S is going to be pretty small and we could approximate if needed. However, if we look at the form of the Q here, there's no like, 0.1 minus S or anything like that that we could approximate or would need to approximate. If we just look at the right-hand side here, this is just going to turn into, a number times X to some power. So we will be able to use an algebra trick. Let's see how that looks. So our algebra trick, if I expand out the right-hand side, again, another place people make a mistake here is we have 2S, that whole quantity gets squared. So it's 2 squared times S squared. So this is S times 4S squared, just distributing the 2 there. And when we multiply that out, we get 4S cubed is equal to 5.0 times 10 to the minus 6. Now, to solve for S, divide both sides by 4. Then we would get 1.25 times 10 to the minus 6 is equal to S cubed. To undo the cube, we can either take the cube root or take both sides to the 1/3 power. So either third root of 1.25 times 10 to the minus 6 is equal to S, or I think it's often a little bit easier in your calculator to find just the generic power key. The way to do that then would be to take S cubed to the 1/3 power, 1.25 times 10 to the minus 6, all that to the 1/3 power as well. And that will also do, because when you take that power, you'll get S cubed times 1/3, so 3 times 1/3 gives you just S to the first power. Either way, you should get 0.0108 molar, or is equal to S, or 0.0108 moles per liter. Remember that solubility is sort of defined as how many moles are dissolved per liter. So 0.108 moles of calcium hydroxide will dissolve in 1 liter of solution. So the nice thing there is that S or X is in fact the molar solubility. We don't have to plug into the equilibrium row to get what we need. That is directly the molar solubility that we were looking for. For mass solubility, if we just use the unit properly, we can see that we have moles of calcium hydroxide per liter, so we just need to do a conversion from moles to grams. So since I have moles, I need to put the thing that I want on top, the thing that I have on the bottom. So what goes on the bottom then is 1 mole of calcium hydroxide, and what goes on the top is 74.09 grams. Again, recognizing that the molar mass here lets us convert from moles of calcium hydroxide to grams of calcium hydroxide, and we get a final answer of Rounding that to 2 sig figs, we get 0.8 grams of calcium hydroxide per liter. The next thing we can think about is this common ion effect. So what's going to happen when we add NaOH to this solution of saturated calcium hydroxide? If you think about that, then you should recognize that NaOH is ionic, so it dissociates into Na plus and OH minus ions. So we're adding OH minus ions. That means the stress is going to be an increase in concentration of OH minus. That's going to cause a shift left. More products, we need to shift left towards reactants to oppose that stress. And when we shift left, what's that going to do? Well, that's going to cause an increase in the amount of the solid and a decrease in the amount of calcium 2 plus. So dissolving a common ion net is going to suppress dissociation, right? Dissociation is the products here. These are the products. When we add that common ion, there's less dissociation, more of the solid stays undissociated, and we can see that since solubility is how much of the solid dissolves, less is dissolved here when we have that shift to the left, so decreasing the solubility. Here's another nice illustration of this for a different equilibrium with lead chromate, this nice yellow solid. Initially at equilibrium, when we add more chromate ion, we get for additional formation of precipitate on the top. For the exact same reason, increase in products causes that shift left, causes us to get more of the solid that precipitates out of solution. So decreased solubility when we add that common ion. Okay, so that was the theory. Now let's actually do the calculation. What would the molar solubility of calcium hydroxide be in a solution with 0.5 molar NaOH, given that same KSP? Now note when we solve this, we don't try to write a new reaction between NaOH and calcium hydroxide. We just have the same calcium hydroxide KSP reaction, but now we're going to have a different initial row of our ice table. So then the way we solve this, using our ice table, going through all the normal steps for solving for equilibrium concentrations, 0.5 molar NaOH, that means that OH minus in our initial point is equal to 0.50 molar. So that's really the only difference here, is we're going to start with 0.5 molar OH minus. Again, our units here are molar. There's none of the calcium hydroxide, but again, the change is minus X or minus S. We're going to dissolve some amount of this calcium hydroxide, and then we're going to make a little bit of each of the products. So 0 plus X, and then again, the 2 coefficient of an OH means we're still going to make plus 2X there. Next, now that we have the ice table, we plug into K equals Q, the same Q expression, calcium 2 plus times OH minus squared, plugging in the equilibrium row. X times 0.5 plus 2x squared is equal to 5.0 times 10 to the minus 6. Now here we have a bit of a problem. This would be a cubic equation if we solved it all out, or if we expanded it all out. But remember that K is quite small here. So since K is small, we expect X is going to be small. X was already in the pure solvent, or in the pure water, only 0.0101 molar, which is quite small. But remember, since there's going to be that shift left, X is really going to be even much smaller than that, what we expect. So therefore, that small x approximation is always well justified for this common ion type problem. So with that then, 0.5 plus 2x is about equal to 0.5. Plugging that in here, now we can see actually there's not even like a square root or anything needed. We just expand this out, do the division to solve for x. So squaring that and dividing both sides by 0.25 to solve for x, we get x is equal to 2 times 10 to the minus 5th moles of calcium hydroxide per liter. Again, we could check our approximation, but we can see that this is much, much less than 0.5. Even the 0.011 would have actually been small enough for the approximation to be valid, and just as expected, that dramatic increase in OH minus caused a large shift left towards reactants and made X even much, much smaller. This often ends up being a relatively challenging problem on the exam, but the reason is really all about the setup. Remembering to just use the same KSP reaction, don't try to write a new reaction involving NaOH, just change the initial row. Then honestly, the actual solving for X part is actually really quite easy because the small x approximation always works well. As long as you just do your couple of math steps pretty carefully, it should be okay to solve for x using just say a square root or in this case, just sort of a algebra step. Here's our first exercise. See if you can do this, and then I'll show the solution. We've got just the sort of Cliff Notes version of solubility rules down below for you to look at. To solve for the molar mass solubility of magnesium hydroxide in pure water, we have KSP, so that's always the reaction we need to write. Just like we need to write Ka for a weak acid, so we need to write Mg, OH2, solid, goes to the ions are an Mg2+, since Mg is in the second group, plus we can see the OH2, that's 2 OH- ions, so 2 hydroxide ions formed. That's step 0. We can also write KSP is equal to Q. That's 5.6 times 10 to the minus 12 is equal to Mg2 plus times OH minus squared. Next, the ice table. Remember that the amount of the solid dissolved is the molar solubility. That's what this minus X or minus S refers to. We started with 0 of the reactants and make plus X Mg plus 2X OH minus. So when we plug in, the Mg2 plus is X, the OH minus is 2X, so X times 2X the quantity squared. Again, in this case, K is small, so we could approximate, but there's nothing to really approximate. We can solve this exactly just by taking the cube root. First, divide both sides by 4. We get x cubed is equal to 1.4 times 10 to the minus 12. Then to undo the cube, take the cube root or take both sides to the 1/3 power. That gets us 1.1 times 10 to the minus 4 moles of magnesium hydroxide per liter equal to our x. Could always go and check it, right? I could plug back into K equals Q. That would be a good idea. In this case, I'm going to go right to getting the mass solubility. So we start with moles of magnesium hydroxide per liter. Then the conversion factor is, we have moles, so that needs to go on the bottom. Grams should go on the top. So times 58.32 grams divided by 1 mole. That cancels moles and gets us to grams of magnesium hydroxide per liter. So just 6.52 times 10 to the minus 3rd grams per liter, a quite low solubility. Doing that answer check here where we plug back into Q, Mg2 plus is 1.1 times 10 to the minus 4, OH minus is double that and has to be squared. We get 5.3 times 10 to the minus 12 for Q. That is, to within some rounding error, basically equal to our 5.6 times 10 to the minus 12, just double checking that we've done everything correct and have found the equilibrium position. For B, calculate the molar solubility in a solution which contains 0.1 molar magnesium chloride. Okay, so again, just the same reaction. The only thing that's going to change is the initial row of the ice table. So bringing back the ice table from the pure water example, now with magnesium chloride, the only thing that's going to change is our initial magnesium concentration. 0.1 molar magnesium chloride means that Mg2 plus initially in this solution is equal to 0.1 molar, because that's the ion that this is going to dissociate into, Mg2 plus 2Cl minus. So we just have to change that. So we now have an initial of 0.1 molar plus x, 0.1 plus x here in the equilibrium row. Then we can plug back into K equals Q. There's plugging into K equals Q. Now we need to choose a method. Again, in pure water, the solubility is 1.1 times 10 to the minus 4. That's already way less than 0.1, but because of that common ion effect, where we increase Mg2 plus is going to cause a shift back left. We expect x is going to be even quite a bit smaller than that. So it is well justified to say 0.1 plus x is about equal to 0.1. Using that small x approximation, 5.6 times 10 to the minus 12 is equal to 0.1 times 2x the quantity squared. Expanding the right-hand side here, we get 0.1 times 4 times x squared is 0.4x squared. Dividing both sides by 0.4 to get x squared by itself, we get 1.4 times 10 to the minus 11. Then the square root of both sides gives us a value of x, 3.7 times 10 to the minus 6 moles per liter. That is much less than what we had in pure water. Double checking the answer with by Q works evaluating well. 5.5 times 10 to the minus 12 is almost exactly the 5.6 times 10 to the minus 12 that we're aiming for within rounding error. Just like we have a table of K and KB, we can have a table of KSPs here. So that's a way to find all these solubility products. Now if we try to understand the meaning, for compounds with the same anion or cation stoichiometry, the larger the value of KSP, the more soluble the compound. So something like AgCl has the, I guess, sort of in the middle here. Let's do AgIO3. That has the largest solubility constant, so it's the most soluble. That means equilibrium is going to go furthest to the right for that reaction. The least soluble is AgI, with a solubility product of only 8.5 times 10 to the minus 17. So again, much less soluble, much lower concentration of Ag and I ions in that solution. Note, though, that if the stoichiometry is different, a larger KSP does not necessarily mean larger solubility. So this example shows that here, where the stoichiometry is 2 ions, 3 ions, and 4 ions. And so even though the 4-ion one has the smallest KSP, its solubility is actually a bit higher than expected. Slotting in right in that middle range between the very soluble BaIO3-2 and the least soluble AgIO3. This just shows that equation in a general way. Remember to always, if you have something with a coefficient of 2 or 3, to take the square or cube root of both parts of it. So 3 cubed is 27 times s cubed times s gives us 27s to the fourth there. Nothing to memorize, but just something to recognize as you do problems with KSP. For the next thing, let's look at when precipitate will form when we mix solutions. So here what we're thinking about is we do some mixture and we want to know if the precipitate is going to form. If a precipitate is going to form, that's going to mean our normal KSP reaction is going to need to run back to the left. We can see that based on just thinking about the equation. If I'm running back to the left, that means Ag plus and Cl minus are combining to make the AgCl solid. So that's what we need, is a case where the reaction goes to the left. That's going to mean basically we need Q is greater than K in order to have that precipitate form. Because again, on our number line, whatever the initial K is, if my Q is bigger than that, I'm going to have a shift left towards reactants. That shift left is going to cause my solid, in this case Ag, what is my solid here? My solid is AgCl, making my solid precipitate out. Next, we can actually show the calculation. Q is Ag plus times Cl minus, because the coefficients are both equal to 1. And then Ag plus, accounting for this dilution, 6.7 times 10 to the minus 3. Cl minus, accounting for the dilution. Again, all these are solved using the dilution equation. MCVC is equal to MdVd. In this case, we're solving for the diluted form here, so Md is Mc times Vc over Vd. And that's what we can see here. It's the concentrated molarity times the ratio of volumes, concentrated over diluted. All that out of the way, we have our value of Q, in this case 1.2 times 10 to the minus 5. So our K here from the previous slide is 1.8 times 10 to the minus 5th. Q is much, much bigger, 1.2 times 10 to the minus 5. So for that reason, since Q is too big, what are we going to need to do to reestablish equilibrium? We need to decrease the concentration of each of these two things. So decrease Ag plus, decrease Cl minus. That's going to mean a shift left towards reactants. So that is indeed what we'll see here. Using that number line, we can see the same thing. Q is too big, so we need to shift back to left towards reactants to use up the added product. This is just reviewing that same information in the number line format. Too many products, so the reaction runs left, forming the precipitate. Whenever I run left towards reactants, I'm going to form the precipitate. If I started over here, since I'm assuming I don't have any precipitate to start with, I'll just sit there and nothing will really happen. One final type of problem we can ask is something like this: who will precipitate first? So if a solution contains equal concentration of these ions and we add the lead nitrate in dropwise fashion, what's going to precipitate first? Well, if we look at it, nitrates are always soluble, so the only choices are lead chloride or lead iodide. Those are right here. Both of those have the same form, so 3 ions, Pb and 2Cl, Pb and 2 iodate ions. But in this case, PbCl2 has a much bigger KSP, so that means its position on the number line, where we achieve K equals Q, is much greater, much closer towards products. So as Q increases, as the lead increases, I'm going to first hit this 3.7 times 10 to the minus 13th, and therefore any of the lead iodate would precipitate out of solution at that point. Now, eventually, once I'd gotten rid of all the lead iodate, then I'd be able to start working on the lead chloride in solution as well. This lets someone perform separations by adding these ions and watching things come out in sort of the order of their KSPs. So first I could isolate all of the lead iodate, and then once all the iodate is out of solution, as I add more lead, I would start precipitating out lead chloride next.